Hi, so we're going to be talking about the DFA to Turing machine conversion. It seems rather unconventional that you would do such a thing, but sometimes this is needed to be done to go from one model to another one, and it's actually relatively easy to do. So it's not really covered, and I will like to cover it here. So let's see, what is a DFA? So a DFA is just a thing where you're provided an input and you go right, essentially. So the Turing machine that we want to basically emulate the DFA should, in principle, just move right. Okay, well, think about how a Turing machine works. So a Turing machine is just this one-way infinite tape, so something like this. So let's say that we're right here, and we said, okay, we're going to move right along the input here. Well, first off, a Turing machine has to write stuff to the tape, right? So it's writing, but the DFA doesn't do any writing at all. So we would need to do something there. And remember that a Turing machine is infinite. So let's say that it ends right there. Well, we have blanks after the fact. So then what we would have to think about is when we hit the blanks, what do we do? So it would make sense, because we're not going back in the input for a DFA, that once we hit here, we should go to either Q accept or Q reject, or accept or reject states, to immediately stop the Turing machine, because effectively that's what the DFA is doing. But the thing is, like, which one should it go to? So let's see. So if we were in a final state of the DFA, so this is in the DFA state, not a Turing machine state. So then in the Turing machine, well, there's no final states other than accept and reject at the very end, those two special ones. Other states are just normal states. So then in the DFA, if we, let's say, had a transition that goes there, then maybe we could stop here, or maybe we could, in principle, keep going. So in principle, we would keep going if we have something to read on the input. So if we're moving right on the Turing machine tape, once we hit the blanks, we have nothing else to read. There's no blanks in the input. So therefore, once we hit the blank, we're done. So therefore, what we're going to do is we're going to redirect we're going to add a transition from each of the final states when we see the blank to the accept state. And we'll handle the non-final states in a very similar way. Okay, so let's see. Let's look at this in a completely formal way and then do an example. So let's say that the DFA here is a set of states Q, input alphabet sigma, transition function delta, Q0, F, start state, final states. Well, let's see. We need to define, for the Turing machine, we need to define some set of states that might be the same, it might not be. The input alphabet has to be exactly the same, because we want it to have exactly the same language. So the input alphabet better be the same. The tape alphabet, we'll define that in a bit. Different transition function, obviously we got to do other things. Q0, the start state, we're not going to change. F, the final states aren't going to translate over, so we got to have an accept and a reject states. Okay, well, let's see. What can we do here? Well, the idea is to have the DFA do its simulation right here. So we have the start state here. So each of the transitions, let's say, looks like this, from one state to another one, let's say on A. Then in the Turing machine version of this, well, so this is not formal, but in the Turing machine, what we want to do is we want to look at that same character and move right. There are a lot of other things you could do here. You could, for example, write a blank symbol there, because we're never going to see it again, so it doesn't matter. So in fact, even if you have a singular DFA on a certain number of states, there are many different Turing machines on the same states, because for each one of the transitions, we can replace whatever we're going to write with something completely different, which is pretty interesting. All right, so what do we do about, let's say, the final states? So in the final states, or as our idea in the now erased part, if we see a blank symbol, we should go to accept, because the blank symbol says we're done reading. And if we end up here and we're done reading, we should have accepted. So in the corresponding Turing machine, note that this state's not final anymore because there's no final states. We would have a blank symbol, let's say move right. You would have to move right in the general case, but you're always safe to move right. So this will go to Q accept. And then from a state that's not final, let's say it's down here, then do the same thing, but go to Q reject. Because if we end up there in the DFA have nothing else to read, we wouldn't accept. So therefore, if we end up here and we have nothing else to read, we shouldn't accept. So it's just a direct translation. All right, so how are all these pieces defined? Well, in the picture, we don't really have any other states except for those two. So I'm going to define all the parts. So Q prime is going to be Q union those two extra states. And there are many other ways you could have defined this. You didn't have to do it exactly this way, but I'm just going to do it this way because it's really easy. So here, I better make sure that Q accept, Q reject are not already states. So these two are completely brand new states. Let's see, so the tape alphabet, we're not gonna do anything on the tape other than with the blank symbol. So the tape alphabet is gonna be the input one, union the blank symbol, where the blank symbol is not in the input alphabet. We better make sure it's not in there. Okay, so let's see. The only thing we really have to define is the transition function. Oh, I would have said that the accept and reject states are not already the start state right here. So these two are not the same as this, but that's fine. We don't need to, because I already said that it's not a state originally anyway, so it's not a big deal. So the transition function on, let's say, a particular state and a particular character, and the particular thing that we, a particular character that we read on the tape, well, this better be exactly the same as what we did in the DFA, except when we have the blank symbol. So this will be delta Q. So this is, I should probably give these subscripts, which is what I'm going to do. So the DFA is equivalent to the Turing machine one for all Q in the original states Q, because the Turing machine doesn't have a transition on the accept and reject states, and A is not equal to the blank symbol. So for every non-blank symbol, it'll just do exactly what the DFA does. So then we got to make sure though. So this is going to be the state that we go to in the original DFA, but in the Turing machine, we need to say what to write and where to go, so, which direction to move. So the thing I'm going to write is exactly the same, no difference, and then the direction I'm going to go is right. Okay. You could say you got to move right no matter what, although there are ways around that, but to make it really easy, I'm going to move right. The thing I'm going to put here, this could be anything. So this thing could be anything. It does not matter what that is. Okay. Okay, so then I had to put subscripts on these. So just to make it easy to differentiate the two. So then for the transition function in the Turing machine, on the blank symbol, we got to define the 3 tuple here. So let's see. So so I'm gonna have this for all Q in the final state. So every final state goes to Q accept, right to blank, let's say, and moves right. And I better erase this so I can fit the rest of it in. That's what she said. So the Turing machine for a particular state on the blank symbol for all Q not in F in the original final states. So that's going to be Q reject. All right, so then let's do an example. So I'm just going to make up a random DFA here. Let's say, so that's a final state. Let's say B, A, oh, that can't go out anymore. So B, okay, so it's just something completely random. So here, the Turing machine says to make a complete copy of the original guy plus 2 states. So I'm going to have, in fact, I'm going to do this in a different color. So this is the Turing machine one. So I'm going to have Q0, Q1. There's no final states now. Oh, this is Q2. I should have labeled it Q2. So Q2. And then we're going to have those 2 extra states. So Q accept, Q reject. This is the start state according to the definition I had earlier. So then each of the transitions will just get adorned with a goes right in the original thing. So here, this is going to be A goes to right, B goes to right, A goes to right, B goes right, this goes B right, A goes right. Oh no, not to the accept state, not yet. And this is A goes right. So this is just a translation of the original transitions. And that's an interesting sentence. So then now from each one of the final states, on the blank symbol, we go to the accept state. So this is the only final state. So that goes to the accept state on blank goes right. And from each of the non-final states, which are these 2, they go to the reject state. So this one goes blank goes right, blank goes right. And that is the transformation from, or a transformation from DFAs to Turing machines. It's a straightforward conversion. It's just adorning right on every transition. An interesting extension to this is to do 2-way DFAs that can go back and forth, which are equivalent to DFAs, something I'll eventually do on the channel. Another interesting you can try to do is to do basically the same conversion, but incorporate some lefts in. So like on these last ones, maybe we want to say the Turing machine can always move left, or allow ourselves to move left at some point. And that almost works here, except if the input is empty. So if the input's empty, you gotta move right, because then the one-way infinite tape doesn't work. So that would be an interesting exercise here. So hopefully that was interesting. Leave thoughts about this conversion into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.